Good afternoon, everyone, and welcome to our fourth Smart Grid Educational Series webinar, hosted by me, Erfan Ibrahim of the Bazaar, a marketplace for digital ideas. We've had three very successful webinars in January, February, and March, and this is our fourth one. We do these on the second Monday of every month from 1 p.m. to 2:30 p.m. Pacific time. Today we have the pleasure of having three presentations, one from UCLA Professor Rajit Gadh, who is also the director of the Smart Grid Energy Research Program, who will be talking about the SMERC research program and what it's doing in the areas of electric vehicle charging, photovoltaics, demand response, and microgrids. This will be followed by a presentation by Klaus who's Senior Director of Engineering and Standards for the Utilities Telecom Council, who's going to be talking about RF safety of smart meters. And the third presentation is going to be by Brett Kilbourne of UTC. He's the Vice President of Government Affairs and Deputy General Counsel at UTC. So without further delay, what I'd like to do is invite Rajit to come and speak about the Smart Grid Energy Research Program that he has at UCLA. And I'm going to be bringing up his slide in just a moment. And I will pass on the presenter ball to him. And unmute him. There we go. Rajit, the floor is yours.
Thank you very much, Erfan. Good afternoon. My name is Rajit Gadh. I'm a professor in UCLA in the School of Engineering and founder and director of the Smart Grid Energy Research Center. Before I get into the details of my presentation, I want to talk about, at a very high level, what has been happening at a national level in terms of smart grid and what are the characteristics of a smart grid that we believe are important and both regionally as well as nationally. One of the important characteristics of the smart grid is its ability to integrate renewables for clean energy and clean environment. And if one looks at renewable energy sources, they tend to be especially wind and solar, which are in California, are coming online at a rather, I would say, at a good pace. They tend to be intermittent. Sun shines only in the daytime and wind blows, in the evenings, and also it's erratic. And as a result, if one wishes to provide baseload with these two energy sources in, let's say, as a substitute for an old decommissioned coal-fired plant, there are challenges. So the grid of the future, i.e. a smart grid or smarter grid, should be able to accommodate and incorporate such energy sources. Energy efficiency, it's very important as we move electricity around from solar to a battery. We go through a process of you're going from DC to AC, AC back to DC, and so on and so forth. And so there needs to be a strong impetus towards energy efficiency. Consumers need to benefit, and I think this is one of the biggest changes that is going to happen with the electric power grid, in which the consumers are going to want and they're going to demand certain services, very much like what happened after the deregulation of the telecommunications industry. I mean, a cell phone today looks nothing like a telephone from the 1970s. Electric vehicles are coming online, just like here in the UCLA parking lot. We have 7 EVs that are plugged into the research platform that we have installed for doing research on grid-to-vehicle aggregation and vehicle-to-grid? And can you use EVs for as energy storage devices on the grid, for instance, or can use them for other applications, perhaps for demand response during a hot summer's afternoon, or perhaps for helping with voltage regulation and things of that nature. Also, when you plug in EVs, and EV is a significant load, so the question is, what does it do to the infrastructure, and what changes are needed at the infrastructure level? Peak demand reduction via demand response is a very important topic. We all hear about it. That's another area of research that we're working on. Utilities are gradually moving more towards variable pricing, time of use pricing, with 3 or 4 or 5 prices in a 24-hour cycle, and that's an opportunity and yet a challenge, because how do you convince a consumer that this can be beneficial to the consumer? National security is important, as we're putting IT, wireless, smart sensors, servers onto the grid, and making it smarter. We want to make sure that things are secure. And finally, better control. If you start taking away the old baseload and generation sources such as coal and so forth, then if you start adding more distributed solar and wind generation sources, and the question becomes, you don't have a heavy inertial system, and so you have all these distributed systems, and the question is, how do you now recreate inertia? Or maybe you want to create inertia in a different way, and specifically, for example, when you're talking about voltage, frequency, current regulation, things of that nature. Our center, the Smart Grid Energy Research Center here in UCLA, organizes thought leadership forums, and I'll give a quick introduction. We invite folks from the different utilities and industry and the government sectors and universities to participate in these forums. We just held one very recently, March 28th, and the next one is in October. The center, we are funded by several different grants. So one of them is a DOE sponsored grant in which Los Angeles Department of Water and Power is the lead, and there are 3 institutions that are partnering with LADWP, and UCLA is one of them. And we have a partners, USC and JPL-Caltech. UCLA is taking a significant role in 2 of the areas, electric vehicle integration and demand response. And I'll talk about that today. The second grant we have is with Korea Institute for Energy Research. It's a 10-year grant. We're just completing the first year, and we're working on several different problems pertaining to smart grid, smart buildings, efficiency, green energy integration. And then we have another grant in collaboration with EPRI. This is a NESCOR grant, and we're a subcontractor to EPRI. And finally, we have what is called the SMERC IPP Industry Partners Program, in which 18 companies are sponsors of our center. We also have what's called the Smart Grid Living Lab. We have UCLA has its own cogeneration by way of a natural gas fired power plant, and that produces roughly 3/4 of our peak consumption, and roughly 1/4 is purchased from the Los Angeles Department of Water and Power. So this makes UCLA a rather interesting ground for doing research, where we where we have our own little micro / mini grid in which we can experiment with concepts like demand response and EV integration and different regulation services right locally here within the campus. We have a leadership council of utilities and some leading thought leaders that help us in some of our thinking in terms of what we need to do here in UCLA. We host some educational and training workshops for industry and communities. And then we finally, of course, publish research papers like any other center. At a very high level, if you look at the traditional electricity flow model, and it has to do with generation at a large scale that provides significant base load, followed by transmission, and then you have the distribution, you have the consumption. And that model in which the power was flowing in one way, the information was flowing in one way, and the control is also flowing in one way, is being upended now with the new generation model in which you actually have some generation that is renewable, in this case, for instance, wind and solar, and that means that when you go take that energy and you want to eventually make it available during the time when this energy is not available, from a generation standpoint, you may have some battery storage on the transmission side. So that's happening, for example, here in California. And that means that the interface between the generation and transmission is going to change. Down at the consumer level, consumers are plugging in EVs, and then they're adding solar on the rooftop. And what that means is that your interface between the consumption and distribution is going to change, because now you suddenly have energy flowing in a reverse manner, and perhaps even information flowing from a homeowner to the distribution level, and asking the distribution level systems to make the changes to be able to incorporate energy that is being generated down at the consumer level. So the consumer has all of a sudden also become a generator. And then, of course, eventually what will happen is if everybody starts producing energy on a distribution side, the interface between the distribution and transmission would also need to change. So there's a lot of different advanced technologies, like, cloud communications, cloud intelligence, wireless communications, sense and control, energy storage, mobile devices, user interfaces, and so forth, that are changing the entire thought process of how grid is structured, which was traditionally one way, and now we have everything is flowing two ways, power, information, and control. The UCLA Smart Grid Energy Research Center, we have a wireless communications infrastructure that is actually, I should say, largely wireless for the wide area communication, and then there is some PLC in certain parts of the campus, such as when a car talks to the local garage, that part you could go through PLC as well as through wireless. But we have this system called the Wind Smart Grid that we have been developing for several years, that connects the buildings, parking garages, and so on and so forth. And the idea is to create a test bed here on campus. Then we have in terms of research areas, like I mentioned, demand response is a key area of research for us, electric vehicle integration into the grid, and the microgrids, in which we are looking at islanding for small regions of the UCLA grid from the bigger grid, and finally cybersecurity. This shows you an overall picture. On the left, you have the utilities distribution grid that goes through the UCLA gateway. Under that, we have the cogeneration. Now, followed by that, we have our buildings, labs, residential halls, parking structures, and then eventually we have our controllable loads. And this is where we are experimenting with bidirectional power flows, bidirectional information flows, and bidirectional control by way of the communications environment that, as I mentioned, has wireless and as well as wireline components. And one of the big things that I think is going on is at the edge of the network. You're down in the where the consumer sits. You have EVs that are sending power back into the grid, and you have solar that is also sending power back into the local grid. And that is actually a little bit more challenging than one can sort of just think about. There are a lot of things you think about. For example, you have to have grid tie inverters, and then you need to have enough capacity. You need to make sure that the transformers can take the energy in the reverse direction, and so on and so forth. So there is a lot of things that actually need to get done from an infrastructure level that we're here in UCLA we're learning as we're doing our experiments. I'll talk about the electric vehicle to smart grid integration research first. So our philosophy is we take the information from the EV owner and operator. That's very critical, I think, that at the end of the day, the grid is going to be smarter because the consumers are going to drive it. So the EV operator is the most important entity here. And then the grid operator, and we've been using this philosophy for several years in terms of our research methodology. The grid operator is also very important, as well as the garage operator, and all of them have to be satisfied with what they're getting out of the investment that needs to go in. The EV owner has to buy a car and put a charging station in their home. the garage operator has to have charging station in the garage and has to find a way to pay for this infrastructure. And the grid operator would like to make sure that the grid will be stable when people start plugging in EVs. I mean, if 1,000 EVs plug in at 8 a.m. in UCLA at the same time, I can imagine there'll be some serious perturbations in our local microgrid, and so you don't want to do that. So the question is, can you create your communications infrastructure in combination with some smart algorithms that are sitting either on the cloud or sitting on these devices that we call charging stations, and we essentially can manage in an intelligent fashion all of these new types of loads that are coming online. EVs today really only take energy from the grid, but the EVs of the future, such as, for example, the experiments we're doing in our lab, will actually send power back into the grid. So, for example, we have a battery array that we're experimenting with in terms of sending energy back into the grid. And there are some significant challenges there as well. In terms of the research, this system that we have been developing over several years, and I know several of you on this telecom have actually seen this system, or this prototypical research system, I should call it. That's what it is. In which with the screen you see here, the EV owner is essentially creating a charge profile using this EV command portal application on the mobile device. So the EV owner plugs in to the charging station, and then they pull up their cell phone, and they can set up their profile once and for all, or they can keep changing it. And then they plug in and they log in, and now our system knows that this is the individual that is logged in, and these are the preferences. And then there's a system side of it, the control center side of it, and that is that could be down in the parking garage like you see in the screen, or it could be up in a control center in which where the garage owner, for example, is monitoring what's going on. In terms of the fundamental research issues on the EV to grid, we take users' requirements and we do scheduling with the user requirements. We do in the garage constraints as well as the utility requirements. Utility may, for example, give a sender requirement and say that, look, today I'm expecting to have a demand response signal between at 1 p.m. and I would like everybody to cut their load by 10%. Well, if that is the case, what happens is that signal comes into our research infrastructure, and then we actually execute that change in the load on the EV charging. Such, for example, if EVs are charging, we'll either cut 10% of the EVs off the grid, or we will reduce the amount of current going in a manner such that the power consumed is down by 10%. So we have these triggering mechanisms, and we take into account user preferences. If a user has to, let's say, leave at 3 p.m., well, then maybe you can't do that to their vehicle. So we take all of that into consideration in our research. The other research has to do with system control and characteristics. When you're creating this wireless communication systems that are there in garages and in campuses, how do these systems behave when you're sending a control signal, and you actually have to measure to make sure that the adequate levels of current are going through when you want them to go through, and so have that entire control system working in a reliable fashion as a research area. Participation by the user is very important, so we're doing some user studies. Price-based control, when you send pricing, instead of, let's say, demand response signal, if you map that to a price-based signal, you can get that. And the ability to offer aggregated services such as frequency, voltage, VAR, things of that nature. Those are some of the other areas of research that we have now started. The next slide shows you the actual infrastructure. Here you can see two of us pointing to this little device, which is a communications device that works either with a commercial charging system or you can just plug in a 110-volt commercial charging system into our device. So it's a commercial 220-volt or a 110-volt charging system. And then we basically are interested in the communications and the control aspect based on what's going on at the larger grid level. And then you can see on the right-hand side, you can see one of the demonstrations that we had last year, and we hold these demonstrations frequently. You can see some vehicles. You can see some EVs that are plugged in right there for testing the demonstration. That's sort of what our platform here looks like. The next slide shows you variable current control charging. So when you're going to a 220-volt situation from the 110-volt picture that I showed you in the previous slide, then you actually have the ability to send variable current into the EVs. So we do that right now, and so essentially you can think of it as a current control device but at a large scale, right? So you could say, well, I want this garage to only have 400 amps, but this other garage can have 800 amps, things of that nature. So you can actually have an aggregated level of control that then we convert it to the microcontrol that goes into the individual EVs. Next slide shows you some of the commercial vendors that for example, have provided us with hardware. We've gotten their hardware for connecting our research platform to. And here you see a picture of the actual battery, lithium-ion battery in the lab connected to the battery management system on the lower level. And we're experimenting with this. It's about a 1.5 kilowatt, very basic system, but to experiment with vehicle to grid. And we're expanding this out now. We're adding more of these to be able to get more power. The next slide shows you the information that a user has to put in. For instance, here's an example, a simple, and we are trying many different interfaces, by the way, so as part of the research. So here you see the user is asked to put in an information that do they want a cheapest method or a fastest method or some sort of an optimized method, and the user picks the cheapest method, and then the system says that, yeah, you'll be fully charged in an hour. The estimated cost is going to be 9 cents, and so on and so forth. So the idea here is to have a very simple set of interfaces that users can use, and then we experiment with what actually is going to work, what's not going to work, and then we take the information from here, and then we come up with our own scheduling algorithm. And the next slide you see is a slide that really is a graphical depiction of the aggregation issue. So if you think about, and as we are adding more EVs to our grid, today we have 7 EVs plugged into our grid, and we are adding at the rate of 1 to 2 per month. We hope that we'll have, somewhere to the tune of about 50 EVs by the end of this year in this local region here in and around UCLA. Well, I mean, if that happens, now all of a sudden you have a very interesting aggregation possibility. Today, if you think of an average, let's say I'm going to use a nominal number of 5 kilowatt, and you have, let's say, I mean, if you have 100 EVs, well, that's nice 500 kilowatts. It's a half a megawatt of addressable load. And when you start aggregating those numbers, things start to get interesting. And so that's the level that we are that we'd like to reach here in and around UCLA in the next, few years. Okay, so the next slide shows you the solar to battery research that we're experimenting with in our microgrid research, and one of our students is showing a demonstration here. So the idea is that if you think about a microgrid, and we think about control systems, you can try direct DC to DC, and so we're trying DC to DC as well as going through an inverter and then back into a battery. And I think that there's going to be room for both. But if you look at, so we basically have a little wireless switch that we provided there that's sitting like on that rod in the picture on the left as a black box, and that you can control wirelessly from anywhere, and then that will execute the instructions that you want depending on which direction you want the power to flow. So if you really think about it, what's going on here is, right, there's information that you get from the grid operator and from the consumer and from the local facility, and you take all that and you perform an optimization scheme, and then you execute the instructions on what's to be done, and actually send those instructions to the control systems, and then they actually do the execution. So a lot of things that are going on in the last mile of the grid in terms of the work that's going on here at UCLA. The next slide talks about the demand response research, in which the utility sends a demand response signal, whether through a smart meter or through a gateway, and then it goes into different classes of load. So right now we're addressing smart appliance control. So we have a refrigerator and a dryer with Zigbee interfaces that we've designed to accept signals from a protocol such as OpenADR and other types of protocols that may be out there. And then there's HVAC controls is the second piece of it, smart load controls and lighting, and then you have the PHEV and the EV management. So those are the areas that we're investigating. And at the end of the day, I think that the entire movement towards Smart Energy Profile 2.0 seems to be, the direction in which a lot of the research labs like ours are going, in the sense that now all of a sudden you have plenty of choices for the IP layer, and so that means your Smart Energy Profile application layer becomes independent, and that's sort of the direction which we're also going. The next slide shows you the home area network. When you have a demand response signal that comes into the home, then the question becomes, how do you then, in the home area network, in the HEN, how do you actually control the different devices and so forth. So we actually are doing a little bit of work on there as well. In the interest of time, I'm going to move forward, but we're doing a little bit of work on Zigbee SEP1020, and so if you look at the slide, and we're doing some work on embeddable control technologies using ATmega 328 and ARM processor for the home area network, and connecting those to solid-state relays and so forth. The next slide shows you the smart energy control algorithm. So once you have a demand response signal or any other type of energy regulation signal that comes into the home, the question becomes, I mean, if you are a consumer, can you set up, once again, going back to the same concept, can you, through a simple mobile interface, set up your own, or through an in-home display device, doesn't really matter, can you set up your own optimization preferences? And for example, you may say, well, I have a higher priority for washing dishes than I have for washing clothes or something like that. So you set up your own personalized preference, and the system will actually react and respond. And so, for example, at the bottom left, you see an LED, so that's part of our test case, and you see a smart plug load that is a Zigbee-enabled plug that actually allows you to do these kind of things today. So the idea is you take these standard interfaces and then you create intelligence around them. I talked of the mobile device for demand response and for other research. So here is an example of a simple interface that was designed to get people involved in, people don't understand demand response, but they do understand energy consumption. So the idea is, how do you get people excited? They do understand being green and things like that. Next slide shows you our little control interface. Again, so from very simple mobile interface in which the consumer can actually send demand response signals to a dryer, a refrigerator, HVAC, electric vehicle, or lighting. So this is a system that's been implemented, again, a research system in the lab. Demand response issues, now that's a little bit more complicated issue because you have to educate people about what it is, what does it mean, and then get them to participate, number one. Number two, even after they've participated, what if when the demand response signal comes, they go and they physically disconnect the loads from smart systems and say, well, yeah, I mean, I knew I signed on, but it's so hot today, I'm not going to participate, or something like that. Or what if, somebody says I have a medical reason, and so it kind of gets, it's not an easy problem. So I think that the solution for this is also going to be complicated. It's going to take some time. So we're experimenting with different models. We're experimenting with price-based demand response, or different types of DR signals, and different types of consumer interfaces and things of that nature, and modifying different types of loads, and also thinking about load shifting and shaping and so forth. This slide just shows you an interesting research project that we've embarked on recently in collaboration with the Korea Institute for Energy Research, and I think that they're doing a really interesting job in the Jeju Island in terms of the infrastructure there. I was there in December, and that's me in front of this a very significant control center that connects with the different elements that they have out in the field. And so that sort of is also a vision that I've had for many years, and we're creating a control center in our lab that we have a very basic version of it ready with a touchscreen, but we are coming up with a more sophisticated version in the next, again, a touchscreen version in the next few months. So that'll be available for viewing by our next conference in October. The city of Los Angeles has been taking a lead role in not only on the smart grid side, but also on the EV side. So Mayor Villaraigosa hosted a workshop here in UCLA about 1.5 years ago, and he spoke, and I also spoke at this event. And there's a lot of infrastructure that is going in here in Southern California region when it comes to, for example, EVs and solar and smart grid. And I think that this opportunity is here. But I think one of the important things is that labs like ours have to do, or other labs also across the nation. Many universities have these similar programs, but perhaps with different emphases and so forth. But when you actually, one of the things we're doing here in UCLA is, we look at where the rubber meets the road. So PhD students are coming up with their algorithms and so forth, but then we actually implement them and you test them at a limited scale. And then we're interested in working with the utilities and other industry partners in scaling up the results that we have. And with that, time is 1:30 p.m., and so I was told to stick to 30 minutes or so. So hopefully I'm on time. I'm done. Thank you very much. Erfan?
Yes, thank you very much, Rajit. And I've asked people to post their questions online. I don't see any questions yet, There have just been logistical questions about the presentation. So all presentations will be distributed in PDF format very soon, within 24 hours of this webinar. So you will receive those. If there are any questions of Rajit, he has an urgent meeting that he has to go to very soon. So I'd like him to be able to answer any questions that you have.
So I can see one question. Erfan, do you want me to address that?
Oh, is there a question? Oh, it must have been sent privately to you.
It's from Gadh at Siemens.
Okay.
Gadh, is it still Siemens? Well, I'll assume it.
Yes, Gadh, yes.
Okay. So, yeah, how does my research relate to, I mean, absolutely, I think that's a really good question. So if you look at what commercial companies like Coulomb and Ecotality and so forth, what they're doing is they're creating an infrastructure to be able to deliver electricity in a safe manner to the consumer and to do the billing. So they're focused on getting electricity to consumers. Our research is we're looking at a different problem. We're interested in aggregation of large number of EVs with the grid operator and with the local garage operators. The idea here is that we take input from these three different sources to be able to schedule. So you can think of this as scheduling in the large, where where you, the user, are one person. So you certainly have to get your needs satisfied, but if you participate in a larger need, perhaps you can get a benefit from it. For instance, if you participate in a DR, suppose there's 1,000 EVs in a neighborhood, in a region, and they're participating collectively as an aggregation in a DR opportunity, well, they may get some incentive. And then what happens is that this information that I would then send, a company like Coulomb can tack on to their billing, things like so. What I'm particularly not interested in billing and those kind of issues. I'm interested in really the core idea here is this aggregation idea. So,
can you repeat the question that Gadh asked? You did not read it fully.
Sorry. The question is, how does your research relate to what is done commercially at companies such as Coulomb Technologies?
Okay, very good. The next question from Warren Stokes asks, he says, what is the single biggest challenge in implementing smart grid? And he's directing that to you, Rajit, as a general question from your experience.
A single biggest challenge. I think there's more than I think there's more than one. Okay, I think the single biggest challenge is the fact that there are more than one challenge, and it's a moving target. And I'll tell you what I mean by that. We are putting EVs online. We are putting solar on rooftops. Just on my street, in the last 2 years, 2 houses have gone solar. And then we are adding wind, in Tehachapi, right in Southern California. We're adding here in the desert area in Southern California. We're adding solar on the transmission side. So, and consumers are taking a more active interest in renewable energy, for example. States are different parts of the world. They want to go clean. I was just talking to somebody in India yesterday. They said there's not enough coal in India, so they're buying massive windmills in India and installing them along the western region where there's a lot of wind in India. So if you think about the biggest challenge, I think, is the fact that everything is changing. And we're having changes at the consumer side, on the distribution side. We're putting smart meters. We have AMI data coming in. We have in the home, people are talking about HN. So things are moving, and they're moving at different speeds. And so I think that we have to think about how all of these are going to work together with each other. So I think standards is a very, very important thing. Simple things like, a smart energy profile 1.0 versus 2.0. Now 2.0 is going to allow different wireless systems to work with an SEP standard. So I think that makes it much more open, much more attractive. So the markets will grow faster, prices will come down, so on and so forth. So I would say that because it's such a complicated business, I think that you have to have things that tie across the different pieces, and I think standards would be the way to do it.
Okay, then I'm going to ask a question from Irene Gasco and then come back to Warren's question. So Irene Gasco from Florida Power and Light asks, are there any security considerations in this project? What is the purpose? Efficiency, reliability, anything else? Focusing on your project, Rajit.
Yes, so, if you think about, we are adding wireless, right? We're adding wireless, we're adding Zigbee in garages, in home area networks. So we're adding wireless to technologies to control the solar array connected to the batteries. And so if you think about these communication technologies, the standard security questions that apply when you use these technologies elsewhere would also apply here. So yes, security is very, very important, and we have to address that. If you think about Smart Energy Profile 2.0, now we're getting into new territories, right? We have an application layer that's independent, then we have the lower layers that are of the stack that are separated out. Well, you have different security concerns there. So yes, security is very, very important. And the question is,
what are security considerations are there in this project of yours? Are you doing anything in the area of security, or is this primarily a communications and data integration project?
Yes, so on the security side, what we're doing is we're not developing our own security protocols because there are other labs in the country who are doing that. So our approach is that we would take, because we've created a very, I would say, a very significant test bed here, and our approach is to take the security protocols that are being put out by others and offer a test bed as a way to test them.
Right. So would you say that your project is primarily looking at the communications and the manageability aspect of these applications, these smart grid applications at the edge?
Yeah, so we look at the interface between the sensors and the communications and the IT backend infrastructure, and then from the IT back to the communications and communication to the control system.
Okay, very good. Because of the shortness of time, and I know you need to go, I'll ask these two more questions. If there are any other questions, please send an email to Rajit and ask him directly. His email address is given on the slide right now. But please don't put any more questions for Rajit because we have to move on to our next presenter. The next question from Warren is, what is the most promising technology for addressing those challenges of implementing smart grid in the context you presented today? So maybe you may want to comment on the wireless technology and how that can be an accelerator, if you may, to smart grid applications.
Absolutely. In fact, Erfan, I was going to talk about wireless because if you think about one of the first things that we need to do is we need to put our finger on the pulse, and that means we need to put a sensor. So we install a sensor, we may install a CT sensor or whatever it is, we may install a Hall effect sensor. We are now we have some analog signal coming in that has to be then converted to digital, and then we send it back to the server or send it back somewhere to a process that can make a decision. So communications becomes very, very critical. And when you think about how widespread our systems are, for example, if you think about in America, the smart meters, most of the vendors are going with wireless and not with PLC like they did in Italy, and because things are all over the place. And so wireless communications, I think, is perhaps wireless communications and how that connects to the data layer, how that connects to the sensors, how it connects to the A to D and the D to A. That piece, I think, is, to me at least, from where I come, from the work we're doing in UCLA, that to me is one of the most important pieces.
Okay, real quick answer to this question in the form of a number. What percentage of electric energy in California is coming from renewables?
It's, okay, I can tell you the City of Los Angeles, because we're working with them on this regional big demonstration grant funded by DOE, the $60 million program. In the City of Los Angeles is about 20% renewables right now. And that's where LA is today, roughly 20%, maybe in the 19-20% range, but that's where LA is roughly today. California, I'm not sure right now. I'm sure somebody in the call might be able to. Maybe Erfan, you could give a more, you can give an accurate number for the state of California.
We're definitely ahead of the national average, which is in the low single digits, but we are nowhere near what our target is, even if we project to the year 2020, we are behind that schedule. So we'll have to take some very aggressive initiatives in order to get to our RPS targets by 2020.
Right. Yes.
Next, two short questions. One from Ramadan El-Moody, who asked, how can you educate non-technical people about the advantages of smart grid? If you could just answer very shortly on that.
Yes, I think we need creative methods to talk to them in the language they understand. That means that if it's a teenager, it's a mobile device. If somebody reads a newspaper, it is through that medium. So I think that the medium is very, very critical, and the language is very critical. And I think that requires people of a certain skill set, which were not necessarily technical people like me, but a different skill set. I think, and as I've been talking to people, and I've realized that's very, very important.
How about some of the forums? You've talked about the technology, but what kind of forums would be good for them?
Do you mean? I'm sorry, I didn't get the question.
What kind of venues? Do you think universities are a good place? Do you think that this should be done through utility programs? How would you approach non-technical people? Because we have to fit into their lives in a way that's meaningful to them. We can't just send them newsletters. They will not read.
Yeah, I agree with you. In fact, I think that, yes, universities can do a certain amount, right? But I think that universities, and then certainly a certain amount of outreach is done. My center, we do lots of outreach programs, but then I think we have to go beyond that. I think, the utilities and the regulators, I think they have to do some of their, utilities, of course, they already do their outreach, and so they have programs in which they educate their customers about smart meters, for example. And so utilities have to do that, but I think also the commissions, the regulatory commissions, or regulatory bodies, I think they also need to do that, because they're talking to the consumers. So I would say that, I would say all of the above.
Okay. And then one final question is from Dave McQuilkin, who says, although the goal of smart grids is to reduce electricity costs, but in reality, time of use and other rate plans will most likely involve increased rates for many people. Are you looking at any social issues related to smart grid deployment?
Oh, yes. Yeah. Okay. So let's first talk about the cost issue. I pay more for my mobile devices and my telephone today than I did 25 years ago. But that's apples and oranges, and I think it's the same. It's going to be the same thing in the smart grid. We are somewhere in the year 1970 of mobile communications today. Okay, that's where we are. So I would say that in the short run, we need to do things that doesn't turn the customer away, and that's very critical. And so, yes, social issues are important. We want to make sure we keep the customer engaged in the smart grid conversation, and so that's the short-term goal. In the long term, 25 years from now, what will the grid look like? Will people think about cost, or will people think about being green? I don't know. There'll be a new generation of people. People who are kids today will be adults at that time. So the world will be a very different place at that time. And the question, I think, is that so we need to get to some place from where we are today, but we have to keep the customer engaged, and we have to do that through social means. And so social issues are important. I do work with sociologists. Our center works with sociologists and gets help from them in designing experiments, for example, demand response experiments. So yes, very critical, I think.
Okay, thank you very much, Rajit, for answering the questions. We appreciate your participation today. And I'm going to now invite Klaus. He's going to be presenting on RF safety. And Klaus, I'm going to pass on the presenter ball to you.
Thank you, Erfan.
Thank you. Can you hear me?
I can hear you just fine. Please go ahead.
Okay. My name is Klaus Bender. I'm Senior Director of Engineering and Standards for the Utilities Telecom Council. The presentation today is a shortened version of a presentation that we've been doing for a while on the impact of smart meters and the radio energy coming from smart meters on humans and the surroundings and where they're placed. And what I want to do today is run through some of the basic science related to RF exposure of humans and the impact of RF energy on human beings. I want to talk about the regulations a bit, and then I want to talk through some statistics on smart meter operations, all related to the safety factor of smart meters and the RF energy that comes from them. So the question that we ask is, why do we care about RF energy? We care about it because we care about the health and safety of the general public. As businesses, we also need to care about it because we need to be compliant with FCC regulations on the devices that we put on our network that transmit RF energy have to be approved by the FCC, and the lack of that approval could have disastrous effects on the business model of utilities. And then we want to be compliant with OSHA regulations and keep our workers healthy and safe. So when we talk about RF energy and its impact on humans, the first and most important piece of science that we need to understand is that there are two types of energy related when you talk about RF in the spectrum of RF energy. We have ionizing radiation and we have non-ionizing radiation. On the screen you see that radio applications and radio operations to the left are considered non-ionizing, and the radio emissions on the right are considered ionizing. And the difference here is very important. You can see underneath the frequency at which those frequency ranges are associated, and at the same time, if you know RF energy, you know that the wavelength is equally as small as the frequency is large. So ionizing radiation is called ionizing because it has a wavelength so small that it can remove electrons from a cell, creating ions without killing the cell first. And so this is permanent biological change to the structure of the cell, and this is the type of interaction between energy and the human body and human cells that we most associate with having cancer. So this is why X-rays, gamma rays, all of these things, your doctor and those workplaces that use that RF energy are very conservative about how you're exposed to this energy, because essentially an ionizing waveform, if it is powerful enough, if it has enough energy, power behind it, can change your cells without killing them. On the other hand, non-ionizing radiation is the type of radiation that we're exposed to every day with our cell phones, our TVs, or Wi-Fi access points, anything that transmits information over a radio signal is generally considered non-ionizing radiation. The primary impact of health on non-ionizing radiation is tissue heating. This is essentially the way a microwave oven works. A microwave oven, it generally heats the cells with the energy until the cells break down and cook. So at lower frequencies, there are also shocks and burns that are possible, but here we're talking about frequencies in the very low frequency range. So again, to review, the key mechanism for injury for non-ionizing radiation is as far as science knows it today, is tissue heating, whereas ionizing radiation, the mechanism for injury is that permanent biological damage that can actually cause cell structure damage and change. Another thing that we need to remember associated with this is that Ionizing energy and its impact on the cells is cumulative. So the more you get exposed to ionizing energy, the more you have the potential for this biological change in your cells. Whereas non-ionizing radiation, because its health impact is only tissue heating, as long as the tissues aren't heated enough to be destroyed, the cells can recover. And so this is, tissue heating in this instance is non-cumulative, and the FCC has rules with respect to how long you can stay in an area that exceeds the maximum permissible exposure levels for a certain type of individual. If you enter the area quickly and leave, there's no permanent biological damage, and this will play into the impact of smart meters in the discussion later as we move forward. So the way the standards were developed with respect to how much energy humans can be exposed to starts with the concept of specific absorption rate. The specific absorption rate is the maximum amount of energy that the body can deal with without having that heating damage, and that through research was found to be about 4 watts per kilogram of exposure over a 5 to 6 hour period. So when the Western standards were developed to come up with a safety level, the people that were developing the standards factored in a 10-to-1 safety level. So most standards related to RF exposure worldwide today understand that the damage potential to the human body is a rate of 4 watts per kilogram, and the safety factor that's built into the regulations is a 10-to-1 safety factor, resulting in a 0.4 watts to kilogram ratio for the specific absorption rate. And when they asked why did we pick the 10-to-1 safety factor, it was relatively arbitrary, but there are points that that you can note is that the maximum specific absorption rate of 4 watts per kilogram is for a healthy person at room temperature. If you're working in an environment where you're on a rooftop where it's 100 degrees and you're standing in front of an antenna array for an AT&T GSM system being exposed to RF energy, then that increase in temperature is going to have an increased impact on your body, and your threshold for being damaged by the RF signal is even greater. Again, not everybody could be considered a healthy individual and may not be in the best physical condition. But this is the basis for the number that the FCC says is a maximum permissible exposure. So if you look at this slide shows the FCC regulations based on frequency, and you'll notice that there's a certain frequency range in the middle where the maximum permissible energy level is the lowest, and that's based on the wavelength of the signal being close to the dimensions of the human body. So the science says that energy of that wavelength is going to consider the body a perfectly sized radiator, or actually absorber of RF energy, and the body's going to absorb that much more energy. Now you'll notice on this graph as well, the FCC levels actually have 2 standards. One is the occupational level, and the other is general public level. The occupational level is that 10-to-1 safety factor level that we talked about before, and the general population safety level is actually 5 times lower than that. So that when you add all that up, it shows that the safety factor built into the regulations for general public exposure, where the person may not realize that they're walking through an area or in an area where there's RF energy, is 50 times more safe than known research says is going to do harm to the body. And that's based on full power exposure. So Again, when we talk about maximum permissible exposure and FCC regulations with respect to smart meters, we're talking about primarily general population exposure because in general, the population doesn't understand that they're being exposed to RF energy and do something about getting out of the area. So if we look at the spectrum of different devices, you can see that there are smart meter devices being deployed in a variety of frequency bands from as low as 450 megahertz up to 930 megahertz and even higher if you count the people that are reading their meters through cellular and PCS frequencies or somehow using Wi-Fi or WiMAX technology. This just shows the different frequency ranges that some of the systems operate on. So if we talk about the regulations associated with exposure, the ones that we're most concerned about are the FCC rules, Code of Federal Regulations, Volume 47. The rule section specifically is 1.1310. It codifies what frequency ranges need to have periodic inspections, what the different frequencies level are per frequency for general and occupational levels, and basically there are different levels that require entities to register and do regular reports, but these entities are generally FM radio stations, et cetera, et cetera. The other documents that are listed there are OET Bulletin 56, Office of Engineering and Technology Bulletin 56, that talks about the research and answers questions about biological effects. And then OET 65 is a document that's essentially the Bible of complying with guidelines regarding RF and human exposure. And again, these documents are written primarily for the target audiences of broadcasters, wireless carriers, and other devices that are transmitting a good deal of wireless energy. When we're talking about smart meters, the smart meter is generally transmitting the same amount of energy or even less as the Wi-Fi access point sitting in your office or the Wi-Fi card in your computer. When we talk about health and safety regulations just for employer-employee basis, everyone should understand that OSHA is the regulatory entity that is responsible for the safety of workers, and their different states enact OSHA regulations a little bit different, but for the most part, OSHA treats RF energy as a hazardous environment and under the general duty clause of their regulations, but there are some specific requirements as far as safety. And generally what OSHA requires is that employees who have to go into a hazardously high level of RF energy receive training and proper instruction on how to protect themselves. So as we summarize the factors of RF safety and the FCC regulations, again, the FCC is the authority for approving and enforcing the RF safety standards, and every smart meter that has a radio module in it that transmits has to meet the FCC rules for safety and human exposure. The FCC rules are based on worldwide documented research of the effect of non-ionizing radiation on the body. Again, we talked about the FCC rules that have the 50-to-1 safety factor for the general population limits. And if we talk about non-thermal effects of non-ionizing radiation, in other words, what about other than tissue heating, we're talking about there's consumer concern, obviously, but the science says that non-ionizing radiation doesn't have enough energy or doesn't have a wavelength small enough to actually cause cancer or any of the things that some of the conservatives are concerned about. So we continue the research. We consider the low duty cycles. and we move on. There's a question on the screen about what is actually tissue heating, and this is actually if you subject your body or anything to enough RF energy, it'll radiate. It'll raise the temperature, exactly the same way a microwave oven heats a piece of meat or a cup of milk. So the standards are based on the amount of RF energy that would raise a cell in your body by 1 degree, and that's considered harmful, and that's where the levels are based on. So if we move on, and now we have a basis to talk about smart meters as far as health effects and the regulations go. What is a smart meter if we break it down into components? A smart meter is a digital device that measures electric consumption. It has sensors inside to tell if the device has been tampered with, or in some instances, what is the power quality. It has an LED display, often as a local area radio network, the smart network that allows a controller that's mounted on a pole top near your house to actually get the information out of that device, or in some instances communicate directly with the utility by use of public carrier frequencies, commercial carrier frequencies. And there are some instances where the device transmits the information over power line carrier frequencies. And some smart meters have a home area network that talks to devices or energy management devices inside the home. Again, another low power technology, generally in the 2.4 gigahertz unlicensed range, which is the exact same frequency range as your Wi-Fi device. And then surrounding the entire smart meter is a big metal box. Smart meters have to go through several regulatory approvals before they can be put on the network. Some of them have to go through ANSI measurements for accuracy and performance. Some of them have to have the NEMA certification so that they can be upgraded. We talked about already FCC standards related to intentional and unintentional radio emissions. There are local codes that might impact the type of smart meter that can be sold. And then obviously there are utility-specific and customer benefit issues that need to be incorporated in the smart meter before the utility will put it on their network. One of the big things that we can factor into the health impact of the smart meter is the fact that smart meters, unlike what some people may believe, are not transmitting constantly. Usually a smart meter will read power in increments between 15 minutes and an hour, and it'll transmit that information maybe every 15 minutes, maybe every hour. So based on 15 minutes, the device only transmits 2% of the day. The messages that are sent from the smart meter could contain consumption information from other meters in the area if those other meters can't communicate directly with the pole top device. They could contain information on a gas meter or a water meter that's in the vicinity in the same residence if there's a utility that is a combination utility. But in general, a smart meter never transmits more than 1 second at a time. Every 15 minutes. So if you take that duty cycle into account and you go back to the slides that talk about the fact that non-ionizing radiation is non-cumulative, you're going to see a situation where there's a small burst of energy that's less than the maximum permissible exposure level for humans in the general population level, and that burst of energy is only for 1 second. So, so bringing that all together, it's the energy that's coming from this device is so low and it transmits for so infrequently that the feared health effects from these devices really can't possibly happen. And in general, some of the devices that are in the home already, microwave oven. If you put a cup of soup in a microwave oven for a minute and stand in front of it, watching it cook, you're getting much more energy than you would get from a smart meter. So these are all factors when we talk about actually what is the impact of a smart meter on humans. So to the FCC, if we talk about regulations now, the smart meter is a computer device like your computer or like other computing devices. It has to comply with regulations around unintentional energy emitted, just like a computer does. If a computer emits too much RF energy into the world, it doesn't pass FCC regulations, and neither does a smart meter. A smart meter also has one or more radio receivers in it. Radio receivers actually use RF energy to do what they do, and so the device has to be approved as a radio receiver. And if it doesn't meet the unintentional radiation levels of a radio receiver device, like your television, like the stereo that's sitting in your office, it doesn't pass FCC regulations either. And then finally, it is a transmitting radio device that for the specific frequency band that it transmits on, it has regulations. There are some meter manufacturers that use licensed frequencies that can transmit at slightly higher power levels. A majority of the smart meters operate at low power frequencies that are license exempt, so they don't have to get a license for each one of them. And so they're generally along the same caliber as the Wi-Fi device or other radio transmitting devices that you generally use. So just to give you an example of some work that we actually did, UTC partnered with an engineering firm and was hired by a utility to actually do some independent measuring of deployed AMI system. The AMI system used 900 megahertz unlicensed for both the downlink from local radio receivers, collection points, hubs, whatever you want to call them, to the meter itself. The meters had built-in Zigbee devices and transmitted into the home. What we found is we took a calibrated measurement device. We got in a utility bucket truck. We went up in the bucket truck at the same level as the collector, and we held a probe 1 foot away from that collecting device, 30 feet up in the air, and constant transmitting. We got only 15.1% of the general population limit. So that's less exposure than the FCC requires as far as the maximum permissible exposure, so to the tune of 15%. When we did the same thing with a smart meter and put it into transmit-only mode and stood a foot away from it, the device, we measured only 14.1% of the FCC's general population maximum permissible exposure. And so if you use the duty cycle calculation as permitted by the FCC and realize that a smart meter is only transmitting at 1% duty cycle, that means the average level, if you average over an hourly basis, average levels of energy coming from a smart meter is less than 1% of the FCC's maximum exposure levels. So we took some Zigbee measurements as well inside the home. And remember, I told you about the big metal box that the meter is in. That resulted in a level of less than 0.02% of the general population minutes of levels measured 3 feet inside the home at the closest point. So, so let's talk about physical limits for a second. There is concern over multimeter installations, and the best example of one of these is a apartment building that has 150 units, and there's a room in the basement that has 150 smart meters. There's concern that people will say, well, if one of these meters is transmitting at 15% of the maximum permissible exposure, at least instantaneously, if you put 150 meters in the room, you're going to exceed the FCC's maximum exposure limit. Well, that's not actually true for a number of reasons. The first is that the network couldn't handle all of those smart meters talking at once, and so when you have a meter installation like that, they're not all talking at once. They're staged so that the utility can actually collect the information from each one of those meters. And one of the things I try and show in the picture is each one of these meters has a physical dimension, and so it's inaccurate to say that you can sum up the power of 150 meters and put it at one point directly where you're standing, because some meters in that example of the meter room could be 8 feet down the wall. And by the time the energy from that meter comes down to you over a distance of 8 feet, it's going to be a fraction of the FCC maximum exposure limit. And again, like I said, don't forget the big metal box. The smart meters are designed, for the most part, to radiate energy out of the front of them to a collection device that's mounted on a pole outside your house. The intent is not to transmit that energy inside the house, and there's a good deal of energy being reflected from the metal box out. Now, if you remember the example of the home area network and the measurements that UTC did, the energy that came inside the house from the home area network was still less than 1%. It's enough energy to actually transmit useful information and make the home area management part of the smart grid a viable application, but at the same time, the energy that comes into the house from the smart meter is a fraction of what the maximum permissible exposure is. So I think the biggest role that we have in educating the public in this is actually educating the public on what the RF energy is, the difference between the RF energy coming from their cell phone, their Wi-Fi access point, and a smart meter, to the RF energy coming from gamma rays and X-rays, and the damage that they can cause as opposed to non-ionizing radiation. We have to also realize that science is evolving. We have to keep looking at non-thermal effects and see if we can come up with anything. We can't just assume that we're always right. We have to continue testing. And at the same time, there are customers that are going to have special needs, that have RF susceptibility, whether that is a perceived issue or an actual physical condition. And utilities can't ignore that. And so, unfortunately, when utilities are working on planning their RF network for reading smart meters, they have to take into account some sort of opt-out strategy for those people that feel that they have RF susceptibility enough that they can't tolerate the smart meter on their house. So, to summarize, I think this is the last slide. Smart meters are a key to the success of the smart grid. They're not the only thing in the smart grid, obviously, but I do believe that demand reduction based on having consumers have as much up-to-date information is a valuable part of the smart grid. Every one of those devices is reviewed by the FCC for compliance with the wireless guidelines. The smart meters use the same frequencies as laptops, Wi-Fi access points, a variety of different RF devices within the home, and have no more health impact than those devices themselves. And when you factor in they transmit at only a fraction of the time, they should be considered very safe, and we should figure out a way to explain that to the public. Here are some references. Erfan said the presentations will be available. The links should be hot in the PDF that we sent. SiteSafe is the company that we did the measurements with for that utility project, but there are some other places that you can look for standards and that type of information. Here's my contact information if anyone wants to contact me and get more information on this. So with that, I will open it up to some of the questions that are on the screen.
Actually, Klaus, I think what would be best is if we brought Brett on and have him do his presentation in the regular time. We are going to go on an additional 15 minutes past our 2:30 p.m. Pacific time to accommodate all the questions, but I would like to get his presentation into the regular time right now, if that's okay.
That's fine with me. Go ahead.
Okay, very good. So I'm going to move to his presentation. And go. And then move the presenter ball over to Brett. Oh, I think it moved back to the original presentation. 1 second. All right. Let's try it one more time. Okay, go ahead, Brett.
Thanks, Erfan. Can you hear me okay?
Yes, it seems a little bit distant, but if you come a little closer to your speaker, that would be great.
I'm going to go to handset.
Wonderful.
That's now. There we go. So I'm going to talk a little bit about what I think is an important issue for smart grid, but that doesn't get enough press. This is having to do with the access to spectrum for smart grid. And let me go ahead and breeze through these slides as quickly as possible so we can leave some time for Q&A. Erfan, how do I go ahead and advance to the next slide? To this one? There we go.
Yeah, if the arrow's on the top.
Yeah. Yes, I did. Sorry, I took a little learning curve there. Real quick about UTC, we're a trade association that focuses strictly on telecom and IT for utility companies primarily and other critical infrastructure industries. We include all types of utilities in the CII. So there's investor-owned, co-ops, and munis. We represent all of those. We're unique in that respect. This is an issue that really hits UTC square between the eyes. And let me go ahead and turn into the spectrum issues that we're facing. As the previous slide mentioned, we've been around since 1948. And the strange thing about utilities as they've evolved over time in terms of their communication networks is it's always been sort of somewhat ad hoc in nature, and they could get away with that for years and years, basically because it didn't matter that what the utility company next to them was doing, as long as they were their networks were reliable. What's happening now is that we have entered into this smart grid era, where it really does matter because we're needing a wider capacity bandwidth. And it's going to be important in terms of creating an ecosystem that's going to bring down equipment costs, that we have an allocation that's in suitable spectrum. And what do we mean by suitable spectrum? We're talking about spectrum that's below 2 gigahertz in frequency range. And that would, to the extent that you've got wide enough bandwidth down below 2 gig, that would provide the kind of coverage that utility companies are going to need to be able to roll out these smart grid services, these networks. In terms of the different sources of spectrum that are out there, I've listed them. We'll talk about these as we go forward through the slides. But the two principal ones I want to focus on are the federal government spectrum and the 700 megahertz public safety spectrum. Specifically, the 700 megahertz public safety spectrum is really important, and there's some new news there that I wanted to go into in detail so that folks that are on the call will sort of understand the lay of the land in terms of the opportunity that exists there for access to that spectrum. So what are the challenges? The problem that utility companies run into as we've tried to deploy these smart grid networks is that the existing land mobile bands that utility companies have used for quite a while, some more recent, but some dating back for decades, is that they're subject to interference, congestion, and narrowbanding requirements, which basically means that the FCC is forcing utility companies and others that are using these land mobile bands to become more efficient, so that these frequency bands have to be narrowed from 25 to 12.5 kilohertz channels. So, basically your supply is being constrained from that standpoint. At the same time, there are other bands that utility companies use for microwave, and those bands happen to be fairly attractive for commercial wireless. So the FCC over the last decade or so has reallocated some of these microwave bands, and when they do, they have to relocate the incumbent operations out of that band. The FCC fortunately has provided a process that provides reimbursement for relocation, but nonetheless, that means that the utilities that are in those bands basically have to move into higher frequency ranges by virtue of those existing bands being reallocated for commercial wireless. And so basically, you can understand that that creates some challenges technically. And then finally, one of the questions that sits out there that utility companies have to answer is that why can't utility companies go out there and just acquire spectrum at auction? And the answer to that is that it's a rather lengthy and expensive proposition. Yes, utility companies to a certain extent do have the resources to be able to compete, but they're competing against commercial wireless providers in a lot of these cases that have very deep pockets and can pass along those costs to their customers very readily. Moreover, the geographic areas of those licenses tend to be either too large or too narrow for utility service territory. So utilities are basically forced with their proposition of buying too much or too little in terms of getting a license through an auction. So that's not really a viable option. And in fact, actually, Congress has clarified that utility companies fall within a class of quote-unquote public safety radio services, and they are exempt from spectrum auctions. So there's a certain principle that's involved here as well, in addition to the practical difficulties of utility companies competing in auction. Congress has basically said that we're supposed to be getting access to spectrum for free the same way as public safety gets it. But unfortunately, the FCC has not seen it that way. So we've run into some practical difficulties as far as that goes. Let me go ahead and go to the next slide. So what are the opportunities? There is the 700 megahertz public safety broadband network. Good news is that we've finally gotten clarification from Congress that non-public safety entities can share that 700 megahertz spectrum. We'll talk about that in more detail as we get further down the slide deck. Another opportunity that exists out there is to access some of the spectrum that the federal government is trying to make available for commercial wireless. They've basically earmarked 500 megahertz of spectrum over the next 10 years that's supposed to be made available for broadband. And in fact, actually, they've already identified the first 115 megahertz, and as part of that 150 megahertz, they've come out with a report that assesses the viability of accommodating wireless broadband in a specific band, that's 1755 to 1850 megahertz band, that actually utility companies have an interest in accessing, as we'll talk about as we get further on. And then there are some other good opportunities, good news for utility companies. Those microwave bands, the FCC now is looking at ways to make them more efficiently used, so that will create more availability for licenses in those microwave bands. And then finally, you can see the policy direction the FCC is heading towards more opportunistic use of spectrum. These are technologies that basically operate primarily on an unlicensed basis that find available spectrum in various different spectrum bands and operate on primarily a non-interference basis. So it creates an opportunity for utility companies to get access in bands that aren't currently allocated for utilities or to other users. All right, so talking about federal spectrum, I did talk a little bit about the 500 megahertz mandate that's come down from the White House in terms of making that spectrum available over the next 10 years. Part and parcel of that, there is a move within Congress to identify various different spectrum bands that might be available for commercial use. That's one move that's going on out there. I think more to the immediate newsworthiness, there is this report that came out very recently about the 1755 to 1850 megahertz band. The reason that report is not only timely but also relevant to utilities is that, interestingly enough, the 1800 to 1830 megahertz band, which is obviously part of this band that the NTIA is looking at, is already currently allocated in Canada for use by utility companies. So we've argued to NTIA and to the FCC that the 1800 to 1830 megahertz band should be harmonized with the allocation in Canada, so that there is a single nation, North American allocation, at least between the U.S. and Canada, which would obviously provide a lot of benefits, both in terms of an ecosystem and also in terms of interoperability between North American utility companies. What we're up against is that the commercial providers do want access, at least in the near term, to the 1755 to 1780 megahertz band, but then, beyond that, they want to try and get the 1800 1850 megahertz band too. So obviously, the 1800 to 1830 megahertz band falls within that range, and of course, as sort of a freeze, if you will, on utility companies getting access in the U.S. to that frequency range. The FCC did release a report at the end of March. I think the interesting headline there is that NTIA concluded that the entire band can be made available for commercial wireless, but it didn't say reallocated. It said repurposed, and it's an important distinction because basically the NTIA is looking at a variety of different methodologies for making that spectrum available, including phased reallocation of certain bands and possibly sharing spectrum with federal incumbents. All right, so next steps for utility companies. We're going to continue to work to promote opportunities for utilities to share spectrum. Ideally, we'd love to get dedicated spectrum. The problem is that, with the federal government having a very hard time finding any available spectrum that can be made available for broadband uses, it's going to make it very tough for utilities to get a dedicated allocation within the federal bands. That being said, we think that utility companies do present a very favorable model for demonstrating that spectrum can be shared with utility companies. So we're looking forward to actually proving that test case, if you will, going forward. The other thing that we're looking forward to doing is there are working groups within SMERC that are promoting shared access to additional federal spectrum. We're going to be working with those working groups. And then also, I think, from a utility perspective, we sort of need to look at other spectrum besides 1800 or 1830 megahertz bands. There may be other spectrum that's roughly contiguous that would still promote economies of scale between the U.S. and Canada, even if it's not in the 1800 or 1830 megahertz band. All right, moving on. So that's it for federal. Let me shift gears to talk a little bit about public safety spectrum, which right now is on the front burner because of legislation that recently was signed into law, passed by Congress and signed into law. But before I get to the legislation and the specifics there, I want to talk a little bit about the spectrum we're talking about from a technical standpoint. It is 20 megahertz total. It's the broadband spectrum between 1763 and 1768 and 793 and 798, combined with an additional 10 megahertz of spectrum that was formerly allocated for commercial as part of the 700 megahertz D block. The only issue really for utilities to access that had to do with some of the legislative language that was attached to this spectrum when some of it was originally allocated to public safety back in 1998. And that language basically said that the spectrum had to be used for quote-unquote public safety services, which it defined as services, the sole or principal purpose of which is to protect the safety of life, health, or property. Now, the FCC basically asked the question, does that include the kind of services that utility companies provide? And we argued that that is the case, that we should be actually able to qualify, because not that utilities are public safety, but that we do use the communication networks to provide public safety services. And that is true because basically we use it on a private internal basis, not commercially. A lot of our guys work in close combination with public safety during emergency response, and even during routine operations, we're using our networks to make sure that the grid is operating in a safe and secure manner. So there are a lot of arguments for declaring that utilities should be eligible to access that public safety spectrum. Unfortunately, the FCC is still considering those arguments, but in the meantime, what happened was Congress did listen to our arguments. We had asked that it clarify this issue, this legislative language that was passed back in 1998. At the same time, we met with various public safety groups, which includes the Association for Public Safety Communications Officials, otherwise known as APCO, the Public Safety Alliance, i.e. the PSA, and the Public Safety Spectrum Trust, which is the PSST. And basically, those public safety groups are, somewhat supportive of our position. So the bottom line bullet point there on the slide is that, ultimately, Congress did pass this Spectrum Act, and it does include provisions in there that clarify that non-public safety services can access the spectrum in combination with public safety. So before I get to the legislation, let me just give you a quick rundown on what's going on at the FCC, just as a status update, and this will make sense when we get into the legislation because it does operate in the background. So the public safety folks have actually been trying to roll out this nationwide network for quite a while. And there are a number of jurisdictions that wanted to go ahead and build out in advance of the FCC actually establishing rules for this nationwide network. And 21 waivers that were filed with the FCC were actually granted, some of which actually included utility companies as well as public safety entities. So that basically put this issue out there in front of the FCC in terms of eligibility, and the FCC did in fact actually ask for comments on eligibility for utilities to share that spectrum. But that's a sidelight. The important issue here is that these waivers are sitting out there, and some were granted, and some are, and actually about 3 dozen more are still pending. Second bullet point, again, with respect to this eligibility issue, there was a technical rulemaking that was initiated back in January, which again, amongst other things, took up this issue of eligibility. So that was something that we also filed comments on in support of utility sharing. Most recently, the FCC has issued a public notice asking the public to comment on what to do with the waivers that were already granted. The question being, can those waivers continue to go forward, given the fact that the legislation basically takes the FCC's jurisdiction to a large extent and gives it to NTIA to oversee how this public safety, it gives it to NTIA, i.e. the FirstNet, to oversee how the network gets built out. All right, so that's a quick snapshot of where we stand in terms of the public safety networks vis-a-vis FCC. Let's turn to what the Spectrum Act actually says with respect to the network. Okay, so there's a couple of very general points I want to hit first, and then we'll get into the details. From a general standpoint, we've already really covered the first bullet point, and that is that the D block does get reallocated to public safety as part of this network. So we're now talking about 20 megahertz of spectrum, not just 10. Secondly, there is a nationwide license that's going to be held by a entity that's created by virtue of this law called the FirstNet. And this entity actually resides within NTIA, and it's supposed to be independent of NTIA, and it's composed largely of public safety folks. But it is going to oversee the construction, operation, and maintenance of the network. In addition, the legislation creates a separate body that's going to set up the baseline technical requirements. That group is going to be appointed by the FCC, and it is going to be composed largely of public safety folks, but also folks with a technical background as well. So you're going to have some commercial wireless providers, manufacturers, et cetera. They're going to be members of that. They've already been appointed. That has taken place, and they are supposed to establish those baseline technical requirements within by May 22nd. We'll talk about the dates as we go forward. Fourth bullet point, I mentioned this before, and it's a big one for utility companies because it does clarify that non-public safety services are entitled to access the network on a secondary access basis. And so the question is, what does secondary basis mean? We're still working that out, but it's an important point because certainly we need to have priority access during emergencies. And then last bullet point, there's an interesting governance provision that basically says that if a state wants to break away from the nationwide network and build out its own network, provided this interoperable with the nationwide network, it can. And so it has to get an FCC approval to do that, but it can go ahead and build out. All right, so I'm moving through these slides as fast as possible, but you know, the bottom line point in this slide in terms of the takeaway is that there is a lot of money that's made available for the build out of this network, but unfortunately it's probably not going to cover the entire cost of the network. And in fact, a lot of this money won't be available anytime soon. And specifically, the $7 billion that's made available is only made available once incentive auctions have taken place and broadcasters have voluntarily agreed to auction their licenses. So there's a lot of question marks as to whether that $7 billion will be available, and if so, when. That makes it really important to have alternative sources of funding for building out this network, which is one of the reasons that public safety is very interested in having utility companies participate. Next slide. All right. I mentioned it a couple of times, the FirstNet and the Interoperability Board. I'll skip through this slide really quickly. Just want to make you aware that if you look at this slide more closely offline, you'll notice that there's no provisions in here that require that any utility companies or utility industry representatives are on either one of these boards, and we think that's unfortunate. You know, given the fact that utility companies have a lot of expertise in running their own networks, and that public safety wants them on board, it's too bad we don't have many positions that are reserved, but we think that there's still an opportunity for us to get access. All right, so in terms of what FirstNet's actually doing, I won't get into too much detail just for the sake of time, but I guess the most important thing to take away in terms of its duties is that it's basically going to oversee the RFP process by which this network gets built out. And so the conceptual idea going forward is that this independent FirstNet body will basically establish standards and will network policies, and also the RFPs that then private entities will use in terms of building out the network. So they've actually got a lot of discretion going forward, and so there's a pretty important group on a going forward basis. In terms of the network policies, for us, the key issues really are, prioritization, access to the network. Those kind of things will be developed, but they will be developed in consultation with the states. So this, the law does reserve a role for the states and the localities to make recommendations with respect to priority access and with respect to the selection of entities that are eligible to share the network. The question is, whether FirstNet necessarily has to agree with those recommendations, but at least there is some opportunity for state and local to provide input into the process. And we think that that's a good thing. We think that utility companies and state and local have a good, close relationship. And, every state and locality is going to have different communication needs. And so to the extent that utilities can help meet those needs on a local basis, that's a good thing. in terms of the process going forward, the important takeaway in terms of these slides is that it's fairly front-loaded. The network itself, probably won't be built out for a couple of years, but in terms of the governance, it's a fairly accelerated process, and so we're trying to encourage our members, the utilities, to get out in front of this process and to engage with public safety going forward. Because if they don't, the fear is that public safety will go its own way. Commercial carriers will basically be the sole providers in terms of building out the networks and actually accessing that capacity that's available on the networks. So what are the issues that are still out there? I talked before about secondary basis conditions that are attached as part of sharing. Certainly we think we can negotiate those issues to the extent that we get an opportunity to do so with public safety. There are preferences within the bill for using commercial infrastructure and also commercial wireless. Our concern there is that those preferences could be interpreted in such a way to basically exclude utility companies from participation in the RFP process. We don't want to see that happen. And we need priority access, especially during emergencies. We also need to make sure that to the extent that we're contributing resources of our own towards this network, that those basically get covered as part of the fees that apply for access to the network. So next steps for utilities, for utilities that are on this call, we encourage you all to be proactive on this. There's going to be some competition out there. This is not something that we can just leave to chance. We need to make this world as best we can. But there's a lot of opportunity out there, and we think there's a lot of flexibility within the statute to do it. So on the whole, we're very excited about this. That's it for public safety. Just to wrap up, there's a couple of other opportunities I want to mention in passing, but nonetheless are still important. As utility companies basically struggle with meeting their existing demands, there are a couple of near-term opportunities they shouldn't overlook in terms of access to spectrum. One is the secondary market. So basically what you're doing is you're acquiring spectrum either in toto or in partial by leasing capacity from an existing licensee that's purchased the spectrum at auction. There are some examples of utility companies that have done this, some successfully, some have run into some issues. There's some lessons learned with those issues. Number one being, of course, do your due diligence. This is one of those things that may serve as an opportunity, but you need to make sure that you do your homework first. There's another opportunity, which is participate in auctions. I talked a little bit before that this is not necessarily the best opportunity, but nonetheless, there are some auctions that are supposed to be coming up that have been put on hold that might actually be something of interest for utility companies. I've basically outlined those here. They're in relatively low frequency bands that commercial wireless probably wouldn't find very attractive from a commercial wireless standpoint. So it might be an opportunity for utility companies to be able to get access to spectrum that they could use for some smart grid applications. And then finally, a lot of utility companies have already turned to using unlicensed spectrum and unlicensed technologies that make opportunistic use of existing spectrum. I've outlined those different opportunities that are out there. Some of them include TV white spaces. This is actually an interesting technology that basically, and rules by the FCC that allow for devices to use up to 6 megahertz of spectrum in markets where there isn't any TV channel in that specific 6 megahertz channel block. So it's a good idea. It's just that there's still some technology development sequences that we have to go through in terms of making this technology commercially available. But there's a couple of utility companies that are actually testing this technology. So you all should avail yourselves of that. And there are a couple other similar types of technologies the FCC is conducting proceedings on. So if you want to try and learn more about those technologies, you can find out more by referencing those dockets that I've listed. And then finally, wireless backhaul. There is the FCC is trying to make more efficient use of microwave spectrum. I mentioned that earlier. I won't go into too much detail here. I just want to make it available for your reference if you want to learn more about that. Final conclusions, again, coming back to the original point, this is not an issue that folks should overlook. This is definitely something that, to the extent that you've actually got spectrum that's suitable, is going to be able to make your smart grid deployment that much more cost effective and timely in terms of its deployment. The issue that we've got, again, is that we really don't have a kind of dedicated spectrum that provides the kind of capacity and coverage that utility companies need. So ultimately what we're looking at this point is sharing, and we need to work with policymakers to make that happen. And then with that, I'll go ahead and open it up to questions.
Yes, thank you, Brett. And just a couple of comments before we move to Q&A. We'll take about 10 minutes for the questions. But on the issue of the spectrum, by having this dedicated spectrum or sharing it with other stakeholders, but not in a complete ISM kind of band, there are several benefits. Brett, you have mentioned some of those, but the security implications of having a hyper-quiet network where it's very easy to do intrusion detection is a real advantage. Another advantage is that as you put the cybersecurity controls that are coming out of the NIST 7628, as well as from the NERC CIP guidelines, it's important to have that extra bandwidth in order to have the latency be low enough for the power system applications to run effectively. And what starts happening as you start piling on application after application in a narrow band kind of a spectrum is that that latency keeps growing. And you may have situations where you have timeouts. So availability being critical in the power systems, if that goes out, then all the cybersecurity controls that support confidentiality and integrity become mute when the application itself is not running. So there are several structural advantages when you move to a spectrum where you can have smart grid applications. You can have a special class of devices that are going to be implemented for communications as well as for network management. You would have more resiliency built into them. The quiet network I talked about is very helpful from an IDS perspective. And then you can think of scaling this infrastructure to the future with more byte-intensive applications in the future. So all of these reasons are behind, from an operational perspective, a real desire to have spectrum like this. So Brett, I really appreciate you telling us and showing us the landscape, what is possible, what's not possible. This is really very helpful. So now I'm going to open it up for questions, and there are a bunch of questions actually for Klaus that I wanted to go through. So I'm gonna, okay, he has unmuted. So let me go to the first question here. Okay, let's see here. All right, so the first question is from Dale Gutierrez, who says cell phone radiation limits are normally specified by regulatory agencies in specific absorption rates, watts per kilogram meter and so on, or watts per kilogram. These agencies often list maximum permissible exposures in amps per meter, volts per meter, or power density, in other words, watts per square centimeter. Smart meters have been measured by EPRI using watts. What's a good scientific argument for the safety and radiation levels from smart meters with this mismatch of units?
Well, I think the question is dead on and points to different sections of FCC rules have different requirements or different specifications for RF devices. So the question does come to what's the best way to judge these, and I believe that it has to be the maximum permissible exposure level, milliwatts per centimeter squared that the FCC uses. in their guidelines for general population and occupational workers. I would agree that some devices are certified by the FCC in millivolts per meter. The SAR regulations is watts per kilogram. It is confusing. But if somebody asks,
would you recommend that an organization like NIST that is involved itself in recommending standards or listing standards, that there be a standard way of measuring radiation from these types of devices so that we have an apples-to-apples comparison?
Yeah, I think that to a certain degree the FCC and NIST need to look at how some of these devices are measured and come up with a more standardized way of measuring. You have to understand these FCC rules are 50 years old and more, and some of the measurement techniques in the FCC rules regarding to their maximum operating parameters are relatively old. Oftentimes, it's merely a conversion, and if NIST doesn't necessarily want to recommend reconstructing the testing process, it might be in everyone's best interest to just have an understanding of how the different units relate to each other, and a simple conversion table might be an answer to the problem.
Or maybe we could have a white paper from the NIST Smart Grid website that shows those translations so that there's a universal site people can go to get it.
Exactly.
Okay, very good. So there's a question, actually there's a comment from Dale who says 10 to the minus 7 volts per meter, and then he says, quote unquote, whispering effect of human membranes. Can you comment on that? Is there something that he's referring to?
I'm not a physiologist. No, I'd have to defer a comment to someone who's more qualified to talk about the biological factors than I. I know what the FCC rules are based on, but I'm not going to try and
okay.
pretend I'm.
I just from the word whispering that it might be low impact.
Could be.
But from Sergio Sagarelli, it says any recent OSHA data on safe level 50 to 60 hertz high voltage fields such as under EHV transmission lines 500 kV and above? Is there any information?
I'm not familiar with any new regulations about that, but I'll take a look into it and see what I can find out.
Great. And then from Dali Kladar, it says, question for Klaus, how far are we from integrated solution, one system for home smart meters for electricity, natural gas, drinking water, and hot water? What would be differences in smart meter wireless communication between these different needs, electricity, gas, and water? Actually, I can address some of this question. The location of gas and water meters is quite different from electricity meters. So quite often, you may want to use a lower frequency communication method to get the gas and water meter data over to an electricity meter, and then piggyback, if you may, on the electricity AMI system back to the utility and distribute that way. That's one way that has been recommended. But Klaus, I'll open it to you.
No, I agree. The industry, as you know, has been moving towards standard communications protocols, and there are vendors now that already make gas meters that can talk to the electric meter, that can talk to the water meter, extending that into the home with standardized energy formats related to washers and dryers and other appliances is also happening. So I think the question is, how far away are we from actually integrating all that? I think we're pretty close.
Yeah, I think that from a data integration perspective, we are much closer than we are from a comms perspective, because on the comms end, having subterranean meters requires a very different kind of frequency than is typically used for home area networks or for neighborhood area networks.
Okay, I agree.
All right. Next question is from Pat Duggan, who says, question for Brett. Do you anticipate less receptiveness to emergency spectrum sharing by much more emergency services personnel and communication densities in dense urban load centers. How best can dense urban utilities accommodate this concern if it in fact exists with emergency services management within their service areas?
Yeah, I mean, the question basically goes to the heart of the issue. So in a dense urban environment, there are going to be potentially more users, hence the reason that public safety may be less interested in sharing spectrum with non-public safety users. I think that there are a lot of different factors that will come into play beyond just the capacity question, not the least of which is this funding issue. So for utility companies to try and overcome that, I think we're better positioned than a lot of the other non-public safety users that are out there. There's definitely a recognition now amongst public safety that they can't do their jobs without electric, water, gas. They need to be able to work in close cooperation with utility companies. So, I guess the bottom line here is don't be discouraged. You may find that even in dense urban environments, the public safety is just as eager to try and share as they would be out in a rural environment.
All right, very good. We just have a couple more questions, and the main reason why we are putting all of these questions here, even though people are dropping off, is that this is being recorded and people can listen later on, and it's important for them to get all the information. So the next question is, are there any good documents in layman terms that can help educate the public on the safety of the RF in the smart meters? How can we educate and satisfy customers unhappy with potential RF hazards?
The UTC has a paper that we tried to talk in layman's terms about the impact of the RF from smart meters. UTC worked with EEI to create a paper as well on that topic. There's research that has recently been done by EPRI and some of the other organizations, whether they qualify layman's terms or not. I'm not really sure, but this is a topic where I think the utilities need to step up and provide some information in relatively simple to understand language, and in the future, in the near future, I believe UTC is going to put an effort forth to make that happen so that we don't necessarily have to get caught up in the differences between microvolts per meter and centimeters per meter squared, and we can raise the discussion level above the unit level and just give an understanding. And I think the best way to do that is to compare the energy coming off of a smart meter with other common devices that are used in the home.
Yes, and to that we have some input saying that the impact of the smart meters is way less than the impact of a Big Mac on the individual health. So apparently those cows in the Amazon jungle that are being grazed are under the influence of some RF waves. Okay, so the next question is, will the UTC measurement report be made available?
No, it's client confidential. The client who let us do the measurements allowed us to use the figures, but would prefer that the name of the utility and the name of the vendor not be used.
Is there a way to anonymize that and just show some data so that people know?
Sure. I think that I have an article in the UTC magazine about it, but yeah, we can do that. I mean, essentially, we could show where the measurements were taken with respect to the meter, what the measurements were, and their impact on the maximum permissible exposure. We might be able to do that. We're working on a program to educate the public on RF safety, and so this is a good suggestion, and I'll see if I can make that happen.
Okay, just a couple more questions to wrap it up. One question from Dale Gutierrez is, why is PG&E still sending human meter readers to some of their smart meters?
My first reaction is you would have to ask Pacific Gas and Electric, but I believe that some utilities opt out policies are if you don't want the RF energy, you can actually turn off the radios. I spoke with the California utility before this call that has actually done that. They have a group of people that want to opt out, and so the utility has to go back to the home to actually interact with the device in close proximity and turn off the radio that talks to the local area network and turn off the home area network. I also understand that some of the opt-out solutions that PG&E uses is actually replacing the smart meter with an analog meter. Why would a utility have to go back and talk to a smart meter or visit a smart meter? I don't know. They could maybe need to reprogram it, maybe need to change some of the settings on the meter that they can't do remotely.
Okay, and then Dale points out that EPRI did a detailed study on Silver Spring network meters, and he says he can send it to me later, so I will then distribute that.
I know the EPRI report is public, and it's a good report. I've read it, so I encourage you to circulate it. It's a good report.
Okay, very good. And then Dale goes on to say, given that cell phone radiation limits are normally specified by regulatory agencies in specific absorption rates, what's per kilogram? Okay, this seems to be a duplicate of that same question.
Yeah.
All right, so moving along, last question by William Miller. We still have not heard enough about white space. There is also a lot of other spectrum that could be used. It seems strange that we keep talking about spectrum that is already reserved for dedicated purposes. Why is the FCC not releasing more spectrum? So, Brett?
The FCC is trying to release more spectrum. It is trying to pave the way for white space types of technologies. You know, it's a slow process. You know, I wish the FCC could do more as far as that's concerned, but you know, they're doing, at least they're doing something. You know, we're running into a lot of issues ourselves. Good.
Yeah, I think the point about sharing with public safety, it seems to be a very natural alliance. Not only is with the sub-gigahertz, the propagation is very good, and around buildings and things like that, so signals, it's much easier to get, especially when you're talking about in distribution substations or in very urban environments where you have to really avoid optical-like propagation of RF. So from that perspective, the sub-gigahertz is great. But then, if you look at what public safety really is, the availability of electricity is critical for public safety to do their job in the event of a natural disaster or any other type of attack. So in that sense, it's very logical to think that an infrastructure that reinforces each other with a communication that carries the application being public safety and the underlying infrastructure being electricity seems like a natural alliance. So what are your thoughts on that, Brett?
I wholeheartedly agree, and I guess the only other point I would make is that, you know, everything you said about sharing is true, and in addition, the 700 megahertz network is going to be based on LTE, and LTE does make it that much easier to share a network because you can assign multiple layers of priority access, so there's a lot more flexibility built into the network, as far as that goes.
So it seems like, you know, what we were envisioning maybe 10, 15 years ago with asynchronous transfer mode is now coming back with multiple, you know, this MPLS protocol and 700 megahertz. So it's a very interesting deja vu here all over again.
Okay. Mm-hmm.
All right.
So
So
it's definitely something that we're checking out.
Any final points from Brett or Klaus?
Nope. Thank you very much for having us. I appreciate the opportunity to speak.
Same here, and I appreciate everyone staying on past the deadline.
Yes, I appreciate everyone staying on the call as well. I am going to now stop the recording, and we will have our next webinar on the second Monday of May. I will be sending the topic in the next week or so. and we look forward to your participation, and we thank all the attendees who have asked us questions and who sat patiently and listened to this. We appreciate the fact that all the speakers between them, they went beyond their regular period, but I thought it was important because this information is very hard to get, and the fact that they all came and shared it with all of you was very valuable and greatly appreciated. So with that, enjoy the rest of your afternoon, and we will be talking soon. Goodbye.